At the core of every modern electronic device, there is a chip called CPU. Without this chip, none of our modern and electronic devices won't work. But the question is, how such an important chip is being made? It begins not with matter, but with logic. Before a single grain of sand is mined, a CPU exists as code. It starts with the instruction set architecture, the language the computer speaks. Engineers write register transfer level code, simulating how billions of logic gates will interact. This blueprint is virtually tested for months before being finalized into a physical layout known as the mask set. Only then does the physical journey begin. It starts in the Earth's crust. We mine silica sand, or silicon dioxide, SiO2, SiO2. But to build a brain, we need purity. The sand is heated to 2,000 degrees Celsius in an electric arc furnace with carbon, triggering a chemical reaction that releases the oxygen as carbon dioxide, leaving behind metallurgical-grade silicon. But 98% purity is nowhere near enough for electronics. We need the 9 nines, 99.999999% purity. To achieve this, the silicon is crushed and reacted with hydrochloric acid to form a gas called trichlorosilane. This gas is distilled and purified, then decomposed back into solid silicon rods using the Siemens process. This is now electronic-grade silicon. Next is the Czochralski process. We melt this hyperpure silicon in a quartz crucible at 1425 degrees Celsius. We lower a seed crystal, a pencil-sized piece of silicon with a perfect atomic lattice structure, into the melt. As we slowly pull it up and rotate it, the molten silicon mimics the crystal structure of the seed, freezing into a solid cylindrical ingot. This ensures that the atoms are perfectly aligned, providing an unobstructed path for electrons to flow. This ingot, weighing over 100 kilograms, is sliced using a diamond wire saw into wafers, typically 300 millimeters in diameter. These wafers are rough and damaged from the sawing. They undergo lapping to flatten them, followed by an acid etch to remove cracks. Finally, they endure chemical mechanical polishing, or CMP. A slurry of abrasive chemicals polishes the wafer to a mirror finish, flattening it to the atomic level. Now we enter the front end of line, or FEOL. This is where the transistors are built. The wafer moves into the cleanroom, a Class 1 environment where the air is filtered continuously. The first step in patterning the chip is oxidation. We expose the wafer to oxygen in a high-heat furnace, growing a thin layer of silicon dioxide on the surface. This oxide acts as an electrical insulator, separating the future circuitry from the raw silicon base. We then apply a liquid called photoresist. The wafer spins rapidly to spread this light-sensitive chemical into a uniform layer, sometimes only nanometers thick. This prepares the wafer for the most expensive and complex step in human manufacturing, photolithography. In modern nodes, we use extreme ultraviolet lithography, or EUV. Inside the machine, a high-power laser strikes microscopic droplets of molten tin, vaporizing them into plasma. This plasma emits light with a wavelength of exactly 13.5 nanometers. This light is blasted through a reticle, a quartz plate containing the blueprint of the chip's circuitry. The pattern is reflected through a series of mirrors that shrink the image by 4 times, projecting it onto the wafer. Where the EUV light hits the photoresist, the chemical bonds break, changing the solubility. A developer solution washes away the exposed photoresist, leaving a physical stencil on the wafer. Now we etch. Using reactive ion etching, the wafer is bombarded with plasma. The plasma eats away the oxide layer, effectively only where the photoresist has been removed. This is anisotropic etching, meaning it cuts straight down vertically, creating deep, perfectly distinct trenches without widening the hole. Once etched, the remaining photoresist is stripped away. We now have the physical shape of our circuit components carved into the oxide. But we need to alter the electrical properties of the silicon. This is done through doping. Silicon is a semiconductor. It conducts poorly on its own. To turn it into a switch, we perform ion implantation. A particle accelerator shoots ions of boron or phosphorus into the exposed silicon at high speeds. Boron creates p-type regions with holes, a lack of electrons, and phosphorus creates n-type regions with extra electrons. The violence of ion implantation damages the perfect crystal lattice we grew earlier. To fix this, the wafer undergoes annealing. It is flash heated in milliseconds to activate the dopants and repair the crystal damage, restoring the orderly flow for electrons. This cycle, deposition, lithography, etching, and doping, is repeated dozens of times. In modern processors, we don't just lay transistors flat, we build them up. We create FinFETs, or gate-all-around transistors. We etch vertical fins of silicon, then deposit a high-K dielectric material over them to serve as the gate. This 3D structure wraps around the channel, preventing electricity from leaking when the switch is off. Once the billions of transistors are formed, they are useless in isolation. They must be wired together. This phase is called the back end of line, or BEOL. We can't just run wires anywhere. We have to build a scaffold. We deposit a layer of insulating glass, etch holes where the contacts need to go, and then fill those holes with metal. Aluminum was used in the past, but today we use copper for its superior conductivity. However, copper kills silicon. If copper atoms touch the silicon transistors, they migrate into the material and destroy its function. To prevent this, a microscopic barrier layer of tantalum or tantalum nitride is applied first to line the trenches. Then, using a process called electroplating, the wafer is dipped into a copper sulfate solution. An electrical charge draws copper ions onto the wafer, filling the trenches and vias. Afterward, a chemical-mechanical polishing machine grinds away the excess copper on top, leaving only the copper inside the trenches. This is known as the dual Damascene process. This wiring stacking continues for 12 to 15 layers. The lower layers connect individual transistors, while the upper layers act as global highways, distributing power and clock signals across the entire chip. After months of processing, the wafer is finished. It is covered with a final passivation layer to protect it from corrosion. Now it moves to testing. A machine called a wafer prober lowers thousands of microscopic needles onto the contact pads of every single die on the wafer. It runs electrical tests to verify functionality. Chips that fail are marked in a digital map. The wafer is then mounted onto a sticky tape and sliced apart using a laser or a diamond saw. This is singulation. The bad chips are discarded. The good chips, the bare silicon dies, move to packaging. The silicon die is flipped over and attached to a PCB substrate. This substrate acts as an adapter, spreading the microscopic connections of the silicon out to the wider spacing of the motherboard socket. An underfill epoxy is injected between the die and the substrate to absorb physical stress. Then, a thermal interface material, often a soft solder or thermal paste, is applied to the back of the silicon die. Finally, the integrated heat spreader, the silver nickel-plated copper lid, is glued on top. This lid protects the fragile silicon and provides a surface for the CPU cooler to sit on. But the manufacturing is done, the process isn't. The finished CPUs go through binning. Because the manufacturing process is so precise, slight variations in the silicon crystal can make some chips perform better than others. A chip that remains stable at high voltages and high frequencies might be sold as a flagship Core i9 or Ryzen 9. A chip from the exact same wafer that has a few defective cores might have those cores disabled and be sold as a Core i5. This maximizes yield, ensuring no working silicon goes to waste. From a mathematical concept to a purified gas, to a crystal ingot, to a wafer, and finally to a finished processor, the creation of a CPU requires mastering physics, chemistry, optics, and mechanics at a scale where the laws of the macroscopic world cease to apply. It is the pinnacle of precision manufacturing, resulting in the engine that drives our modern world. And that's it. This is how CPUs are made. If you enjoyed the video, please give thumbs up and hit the subscribe button. Stay tuned till next video.